Hello, welcome to this course on modeling, analysis and estimation of three-phase unbalanced power network. In the last lecture, we have derived the zero sequence, positive sequence and negative sequence impedances of a fully transposed line, and we have also basically derived the expressions of those impedances in terms of their physical dimensions as well as the wire resistances. So now let us look at some numerical example. So we considered the earlier line. Again, we consider the earlier line, that is, we considered the earlier line that we had this, and these all these data and everything we have already given. So we are not again reproducing them unnecessarily. So I am just simply for cross reference. So this was phase A conductor, phase B conductor, phase C conductor. This is 10 feet, this is 10 feet, this is 45 feet, this is 15 feet. And so this was the line we have considered, and for this line we have essentially considered two cases where basically case one was that where there was no transposition at all, and also the second case was that where there was some transposition, but then the values of S1, S2 and S3 which were not equal. And please recollect that this length of this line we have taken as 40 mile, and the other dimensions are already given in one of the lectures, so we are not again repeating them. So here we are going to consider the case of fully transposed line. So that means here we are going to consider that S1 is equal to S2 is equal to S3 is equal to 40 by 3 mile. It is just the case. So here, as we have already calculated, so the value of ZS for a 40 mile length we have already calculated. So this is 14.932 plus J 58.376 ohm. So that we have already calculated, so we are just simply recollecting them. Now to calculate Z0 and Z1 and Z2, we need to calculate Zk, and to calculate Zk we need to calculate Deq. So Deq basically D12, so it is Deq, so it would be D12, D23, D31 cube root. So it would be D12 is of course, so this is position 1, position 2, position 3. So it is 10 feet, then D23 is 10 feet, and then D31 is 20 feet cube root. And if I do this calculation, it turns out to be 12.6 feet. That's what it turns out. And R A value we have already taken to be 0.05928, and so Zk would be essentially that 0.09528. I mean, R basically this value of Ra we have already also mentioned, so we are simply again using it. And omega k value we have already said that it is 0.12134, so it is J 0.12134, that we have already said. Log DE was 2790 divided by 12.6 into, and we said that it should be multiplied by S, so it is multiplied by 40. So if I do this calculation, it turns out to be 3.812 plus J 26.211 ohm. So then therefore my ZABC would be simply that 14.932 plus J 58.376, then 3.812 plus J 26.211, then again 3.812 plus J 26.211, and of course it will be a symmetrical 3.812 plus J 211 14.932 plus J 58 and 3.812 plus J 26.211, and it would be also 3.812 plus J 26 point and 14.932 plus J. So this is my ZABC matrix for a fully transposed line. So this is for fully transposed line. So if I now calculate Z012, it turns out to be 22.554 plus J 110.79, and then 0, then 0, then it is 0, 11.12 plus J 32.166, 0, 0, 0. So this is for a fully transposed line. So this how, so then therefore how this calculation will be done. This calculation essentially involves most of the earlier calculations. Only extra thing need to be calculated is the value of DEQ, and the illustration of calculation of DEQ is this. Now let us talk about another concept called twisting. Twisting is essentially, in the case of transposition, all three conductors change their positions for corresponding to phase A, phase B and phase C. All these three conductors change their position. But in the case of twisting, what happens that only two conductors change their position. For example, suppose I do have this kind of a case that, for example, so this is position 1. So let us say that this is position 1, position 2, position 3. So I say that these are position, and let us say that these are phase A, phase B and phase C, and then after some time these conductors change their position. So, how does it look like is that after some time, so this is A, this is B, this is C. So, this comes here, this comes here and this position comes here. So, then therefore, what happens is that when that happens, so that means after some time when this happens, so then therefore, these conductors become A, C, B. So, it is called twisting. Please note phase A conductor has not changed its position, it still remains at position 1, but after some time or rather after some distance phase B has assumed the position of 3 from its original position 2 and phase C has assumed the position of 2 from its original position 3. So, then therefore, this we call a case of twisting of positions 2 and 3. So, then obviously, we can also have another case of where the twisting of positions 1 and 2 take place, and also there can be a third case where the essentially the twisting of conductors in position 1 and 3 take place. So, these 3 cases are possible. Now, how do I represent this operation of twisting? So, that is very by a simple matrix. So, we call it a twisting matrix, and that twisting matrix can be derived in a very simple manner. So, suppose I take an I3, that is the 3 cross 3 identity matrix. So, this is a 3 cross 3 identity matrix, and then from this 3 cross 3 identity matrix we find out the twisting matrix corresponding to interchanging of conductors 2 and 3, or rather the corresponding to interchanging of conductors in position 2 and 3 by interchanging the columns of second and interchanging the second and third column. So, then therefore, T2 T5 2 3 would be 1 0 0. So, first column remains same, third column comes into the second position, second 0 0 1, and it becomes 0 1 0. Right. Now, let us see what is the effect of this. Now, if I, for example, if I, now you see if this is A, B, C, so then initially it was IA, IB, IC, but after these two conductors have interchanged position, they have been twisted. So, it now becomes IA, IC and IB. Does it now? Of course, that same thing is also getting reflected here. For example, if I write down T523 into IABC, that means T523 is 1 0 0 0 0 1 0 1 0 and IA, IB, IC. I find that this vector becomes IA, then becomes IC, then becomes IB. That means it becomes IACB. So, you see these two conductors B and C, they have interchanged their positions. So, B and C became CB, IACB. So, this matrix T5 to 3 essentially mathematically reflects essentially the twisting operation. Now, in the same manner, if I talk about twisting matrix T phi 1 2, T phi 1 2 means that the twisting matrix corresponding to interchanging of position 1 and 2. So, then so in that case what will happen? Column 1 and 2 will interchange their position. So, then therefore, column 2, original column 2 will become column 1 0 1 0 and 1 0 0 1 0 0 and then 0 0 1 0 0 1, right. So, that would be twisting matrix. And then similarly, of course, T phi 1 3 would be nothing but that column 1 and 3 they will be interchanging their positions. So, it will be 0 0 1. So, third column, original third column will come to the first position. So, second 0 1 0 and then 1 0 0. So, you see, so just by the original 3 cross 3 identity matrix, we can very easily find out the corresponding twisting matrix. Now, this twisting matrices has got a very interesting property. Let us see that what happens to T phi 2 3 whole square. If I do twisting matrix square, that means what is physical interpretation of the square of this twisting matrix? The physical interpretation of square of twisting matrix is that we are applying the twisting operation consecutively. So, what happens? So, T phi 2 3 is 1 0 0 0 0 1. So, 1 0 0 0 0 1 and then 0 1 0 0 1 0 and then the same thing 1 0 0 0 1 0 1 0. So, it becomes 1 the first and then 0 0 then 0 then 0 then 1 then 0 then 0 then 0 then 1. So, this is the identity matrix. That makes sense because if I do apply the twisting operation consecutively, for example, if I apply T phi 2 3 once, so that means position 2 and 3 will interchange their position, and then again if I do apply T phi 2 3 again, so then therefore, now position 3 will again assume the position 3 and position 2 will assume the position 2 again. So, then therefore, after the first twisting operation, conductor 3 will go to position 2 and conductor 2 will go to position 3, and again after the next twisting operation, conductor 3 again will come back to position 3 and conductor 2 will again come back to position 2. So, that means assuming the original configuration. So, obviously, and this original configuration is represented by this 3 cross 3 identity matrix. So, it will be I 3. So, then obviously, from the same token I can also write that T by the same property T phi 1 2 square is equal to T phi 1 3 square is also identity matrix. So, using these three properties I can also write that T phi 2 3 is equal to T phi 2 3 inverse. So, then therefore, This matrix T phi 2 3 is also its own inverse. That matrix does not change. T phi 1 2 is equal to T phi 1 2 inverse, and T phi 1 3 is equal to T phi 1 3 inverse. So, this simple property can easily be written down. Now, let us see that what is the application of this. Now, how do I utilize these matrices for the analysis of the our lines? Now, let us see that, let us consider a case that I do have three conductors, phase A, phase B, phase C, and this is position 1, position 2, position 3, and this is position 1. So, this is position, and so then therefore Z 1 2 3 I can simply write down Z 1 1, Z 1 2, Z 1 3, Z 2 1, Z 2 2, Z 2 3, Z 3 1, Z 3 2, Z 3 3. Now, if I now do an operation pre-multiply, now if I now T phi 2 3 into Z 1 2 3, what happens? What happens if I do this operation? So, it becomes 1 0 0 0 0 1 0 1 0, then Z 1 1, Z 2, Z 1 3, so what would be that? Z 1 1, Z 1 2, Z 1 3, and then Z 3 1, then it would be Z 3 2, and it would be Z 3 3, and then it would be Z 2 1, Z 2 2, Z 2 3. So, then what happens here essentially? Essentially, when I pre-multiply this matrix Z 1 2 3 by T phi 1 2 3, essentially the rows, essentially second and third row has been interchanged. So, then therefore, this is, so then therefore, if I say that, so then therefore, I can say that if I multiply pre-multiplication by T phi 2 3 interchanges row 2 and row 3 of Z 1 2 3 matrix. Similarly, pre-multiplication by T phi 1 2 1 2 would be interchanging of first row and second row, and then so Similarly, I can say that interchange first and second row, and T513 is interchanged first and third row. So this is the case of pre-multiplication. So this is the case of pre-multiplication, right? Now let us look at that what happens if I post multiply the matrix Z123 by T523. So what happens post multiplication? So post multiplication. So post post multiplication, what happens? Post multiplication means what I am trying to do is Z123 into T512 T523, say we should take T523 T523. So Z123 Z11 Z12 and Z31 100, and it would be 001 010 001. So what it would be Z11 and then Z13. So the Z13 and then Z12, Z1, then Z23, then Z22, Z31, Z33, Z32. So what happens here? Happens that here essentially column 2 and column 3 have been interchanged. So that means post multiplication interchanges second and third column of Similarly, if I post multiply by T512, it would be interchanging post multiplication T512 interchanges first and second column, and if I pre-multiply by T513, it interchanges first and third. So these are the basic properties of this. I mean, essentially these are the basic properties of this twisting matrices. So we will apply these basic properties of these twisting matrices for the analysis of our transmission line in the next lecture, followed by one example. Thank you.